Welcome to Chapter 2 of this class on PDEs. In Chapter 1, we gave you the definition of an ODE and we discussed ODEs. Today, let me give you the definition of a PDE. A partial differential equation is an equation that relates a function with its derivatives with respect to d variables, and the unknown is a function. Of course, if d is equal to 1, that is called an ordinary differential equation, and again, this is what we discussed in Chapter 1. Now, let me give you a few examples of PDEs. Minus Laplace u equals f will be a PDE, and the Laplace operator means the sum of the second derivatives. So it's the sum of the second derivative of u, with a negative sign on top, in front, is equal to f. That is a PDE. The time derivative of u minus the Laplace operator applied to u is equal to f. And that's another PDE. And the second derivative of u with respect to time minus the Laplace operator applies to u is equals to f is also a PDE. Obviously, the Laplace operator is important, and we will basically discuss the Laplace operator a little bit in this chapter. Let me tell you what we're going to do in this chapter 2. The goal of the chapter is to first review a few things regarding differential calculus. And most likely you already know most of the material of that section 1, but it is here so you can basically skip it, or you can go through it in high speed, fast forward through it, make sure you know everything. That's important material for the rest of the class, but most likely you already know it. Then the second section will be a few definitions and classification of PDEs. We'll explain what is an elliptic PDE, what is a parabolic PDE, what is a hyperbolic PDE. And again, we explained in the introduction of this class that we will only deal with elliptic and parabolic PDEs in this core class, and that hyperbolic PDEs will be for next year, should you choose an elective class on actually to go further with PDEs. So it's interesting to know what is elliptic, parabolic, and hyperbolic, since that's things that we're going to do in this class. And then we will see how we can model with PDEs. We will derive the heat equation, so we'll explain to you how we can start with physics and derive the equations that will model the evolution of the temperature in a cavity, and we'll actually choose a reactor, and we'll see how we can actually start with the physics and go all the way to the equations. And actually, once we have these equations that we have derived today, then in the next chapters, what we could do is work to figure out if the equations have solutions, and then possibly numerically approximate the solutions. So we'll do that in chapter 3, in section 3 as well. Let me be a little bit more precise on what we're going to do in each section. Section 1, we're going to discuss the outward normal vector field. We're going to discuss partial derivatives, and we're going to discuss the integration by parts in higher dimensions. And again, that is mainly a review. Most of the material which is presented is already known by most of you. Second section, we will talk about the types of PDEs. Again, elliptic, parabolic, hyperbolic, also the order, the linearity. And we will discuss the well-posedness of PDEs, and we'll also explain what is a boundary condition in that section. And in the third section, as we said, we will first talk about the temperature in a reactor. We'll also give a model for the air pollution traffic flow. That will actually be a pretext to talk about the characteristics of the PDE. And we will finish with Black and Scholes, which is an equation which is quite useful in finance.